Okay, so we are going to look at the Sarno landslide, debris flows. Okay, well you are. So this is the photograph of them, 1998, overnight, in May. Some big debris flows you can see here, cascaded down this carbonate platform in volcanic classic deposits and killed about 144 people. And your task is to, well, luckily, I've got some imagery of the landslide just after they happened. So I've got some Google Earth imagery where you can see the extent of the debris flows a few months after they occurred. So we can do some analysis of these landslides. And so basically, we can first of all map them, which is quite nice, and we can also generate what are termed mobility indices. So we can start to look at generating things like run-out prediction models for these landslides, which is what you're going to do. So the way the landslide models work is if I'll show you my little wonderful diagram. I didn't draw this one, somebody else. Okay, so this is really good. This is myself and Derek in Queen in a town. I'm not sure when it was. It's probably about, I reckon, about 8 years ago. And you can still see the remnants of the debris flow in the town. And by that I mean mud plastered against the wall, tiles embedded in the wall, scour marks on the walls from the debris flow. So scour marks on the walls from the debris flow itself as it came into the town. And you get an idea of the thickness of the deposits. So you can see here sort of spatter of mud on the walls following the event. But what's quite good here is that Derek Rust is quite tall. He's about 2 meters tall, I'll say, approximately. So how thick was that deposit as it entered that town? There's there. There's the top of it. So that is what? 2, 4 meters, at least 4. Is it a uniform thickness or does it vary? Well, it's quite thick here. Yeah. Up there on the balcony, back down again. So the thickness of the debris flow is varying quite significantly as it enters the debris. So it gives you an idea about, if you look in these rooms, for example, you find they were filled with mud, completely filled with debris. Yeah. So I'm not sure what's happened to this party. So what I want you to do is, using the data I provide, where is it? There we go. It's a volcano, but that's just because it's the best I can find. What I want you to do is essentially work out a mobility index, which relates the length of the landslide, okay, the total length, to the height difference between the top and the bottom of debris flow. Okay. There's also a calculation based upon the volume as well. Okay, and these are used quite a lot for the hazard assessment when it comes to debris flows. Okay, so I've given you data. I'll show you. I've given you imagery, and I've given you elevation data. So you can work out height difference. You can work out length. Okay, I've given you volumes data, so you can start to generate some of these parameters for yourselves. Because this is how you would assess the hazard and risk to an environment where you've got this type of problem. So it's on the Google Drive. So the town of interest, or the towns of interest are Queen, I can't say it, Episcopia, my terrible spell. And town of Sarno. So essentially, this whole region here was affected by the debris flows. Okay. So I've given you imagery of them, which you can hear. I'll show you. Okay. And if you zoom in, you can see the debris flows themselves. Okay. So we can see the tracks of them here. See the source. Is the termination point of all of them that occurred after this particular event. It happened all the way around the platform, particularly in Quinditch in the north as well. And your task is to map these, to work out the height difference, etc., etc. What I also want you to do, which is very interesting, is for you to look at what they've done to mitigate them in the future. Because do you think this kind of event might happen again? Got the same geology, you've got similar catchments that haven't been affected. Okay, do we think it might happen again? Yes or no? Nice. You think so? When? Who knows? Why did it happen? Okay, so when you read the handout, it explains, but essentially you've got a carbonate bedrock, you've got Mount Vesuvius not far away. So what's this thing covered in? Ash, yes. But not ash from just one event, ash from lots and lots of events. It's got ash, it's got paleosol, weathered surfaces, more ash, weathered surfaces. And so basically what happened was there was a massive period of rain over a long period of time, and then a really big downpour. Okay? And that downpour essentially basically mobilized these debris flows. There's some arguments about what triggered them, but I want you to pay attention to where the debris flows started, because you often find they started where people were building tracks on the scarp. Yeah, they cut some tracks, they cut down trees. Okay, so in some cases that may have triggered. But essentially, it was the big rainstorm mobilised the materials. So it's going to happen again. I would like you to look at what they've done since, and the way to do that is in the handout. I've given you a link later. I hope it works. Where is it? Yeah, here we go. Okay. So I've given you a Google Map link to the same site now where you can see what they put in place. Yeah. So these were the channels along which the flows came. Okay. And they've done some massive construction. What have they done? What is it? Yeah. You think it's as big as a stadium, but it isn't a stadium. Okay. So let's just zoom in and have a look. So the first thing they've done, can you see these big white channels? Yeah. So what are those channels doing? They're catching and channelizing deposit, aren't they? Yeah. So that's the first thing. So they put in big concrete channels to channelize deposit, to catch it and to funnel it. Okay. So why would you concrete a channel with debris flow? What does debris flows do? Debris flows are very interesting processes. They what's termed bulk. So as they come down a slope, they entrain other material. Okay, and they get bigger as they come down the slope. As they're coming down, they're eroding, more materials coming in, and they get bigger and bigger and bigger. Okay? So if I concrete a channel, can my debris flow now bulk anymore? No, it can't. Can it? Can't pick up any more new material, which is a good thing. What about the slope angle? What's a good thing to do about debris flows? What do you want to do with the slope angles? Decrease them, yeah. So you find the channels themselves, they try to decrease the slope angle, to slow the debris flow down. Now, on the base of your channel, do you want your base of your channel to be like a mirror, lovely and smooth, or do you want it to be really, really rough? Which? If it's really smooth like a mirror, my debris flow is going to do what? It's going to accelerate, isn't it? Yeah, it's going to go shooting off down. It's called the friction. We want to make it as frictioned as possible. And if you look, what they've done, they've made the bottom of the channels as rough as possible to try to slow the debris flow down. So reduce the angle, make the channel really rough, and they've also put in other, what they term sacrificial mitigation, which are things like big metal bars, okay, which are designed to take the impact debris flow. They'll be destroyed, probably, but they are there to try to mitigate. So they put a whole suite of mitigation. Really, really interesting. What do debris flows do is go around a corner? No. As debris flow is going down its flow, does it go around a corner like that? Or does it sort of do that? In what terms super elevates? As it goes down the slope, it goes around a corner, it goes up at the side. And so what happens is, the stuff at the side goes up and over whatever obstructions in the way. So that can be a problem as well. So they try to mitigate that super elevation that occurs as debit flows go shooting around corners. So I do urge you to look at that because it's really interesting. Go north to Queenditchy, have a look what they've done, because they've done some fantastic. And it's huge.
His target audience.
What's that?
If you look up, it's like highlighting all of the clubs and places.
So this is what's termed a retention basin. Okay, it's not a stadium. So what it's designed to do is designed to retain any debris that enters it. Okay, so to try to stop it from entering the town. Okay, and that's why it's so large. And that's why all these channels here essentially terminate inside that channel. Have a look at it, because it's really quite amazing what they've done. Try to mitigate it. Okay, so that's me finished. So the data you need is on the Google Drive. It's all ArcGIS compatible, so you'll be able to load it and look at the data. And the handout exercise also explains is on Google Drive. Your enthusiasm. I hope you've enjoyed it, and Portsmouth. Yeah. Good.